there are two things that we have to get to from this thing that we've worked out here. The first is, I want to talk a little bit about Ka, this acid, this K acid. And as you know, it's a fundamental chemical property of the acid, right? It's determined, the dissociation extent is determined by the chemical properties of what makes the acid. The second thing that I want to tell you about is that if we know Ka and pH, this is the important thing. If we know Ka and the pH, then we can calculate the relative ratios of the undissociated acid, HA, and the conjugate base A minus. Okay? Let's see how to get there. Okay? Now, you would agree that we agreed that Ka, being a dissociation constant, reflects H plus A minus over HA. This is just a statement of chemical equilibria. And I can take the minus logarithm to the base 10 of this side and of this side, and look at what I get. That the proton concentration is equal to Ka times HA divided by A minus. And now I'm going to take the minus log 10 of this. And that will give me minus log 10 of proton concentration is the pH. And that is therefore equal to minus the log 10 of the Ka, which you guys told me was the pKa, right? And then it's going to be minus the log to the base 10, right, of HA over A minus. And I'm going to rewrite this like this, that the pH is equal to the pKa plus the logarithm of A minus over HA. All I've done is to remind you that if I flip the numerator and denominator, that's the same as changing the sign of the log. Okay? And this equation you will use again and again and again in your career. This equation has a name, right? It's called, and again, this equation is called the, anybody know? Yeah, of course. This is the Henderson Hasselbalch equation. And the way I want you to think about it is, says that the pH is the pKa plus the logarithm here of the proton acceptor concentration divided by the proton donor concentration. Okay. Okay. Well, what does it tell us? It only tells us the ratio of that conjugate acid of the acid to conjugate base. It doesn't tell us the absolute amounts. It only tells us about the ratio. So let's go back now to acetic acid. You know that acetic acid, I've told you, has a Ka of 1.75 times 10 to the minus 5 molar. And if you take the minus log to the base 10, this means that the pKa is 4.76. That's the pKa for acetic acid. Okay? And what this means is, what does this tell us about acetic acid, a solution of acetic acid at different pHs? Okay? So suppose I have a solution of acetic acid, and the pH of that solution is 4.76. Okay? What does that mean? Well, 4.76 is the pH, and that equals the pKa, 4.76, plus the logarithm, right, of the acetate anion divided by the amount of undissociated acid. So what's the ratio of the conjugate base to acid here? 1, right? This ratio must equal 1. because the log to the base 10 of 1 is 0, and 4.76 plus 0 is 4.76. So what this means is my solution of acetic acid at pH 4.76 has an equal amount of the undissociated acetic acid and the acetate anion. If the total amount of acetic acid in the solution is 1 molar, then I have half a molar of acetic acid and half a molar of the acetate anion. If the solution is 10 millimolar, then I have 5 millimolar of the undissociated acid and 5 millimolar of the acetate anion. Okay. What about, suppose I'm 1 pH unit greater than the pKa. Okay? So now I make my solution, and it has a pH of 5.76. Okay? Well, what does that mean? Well, that has to equal the pKa plus the logarithm of the acetate anion over the undissociated acid, HAC. Okay? So what does this ratio now have to be? Yeah, somebody. What's the ratio? 10 to 1, right? This ratio has to be 10 to 1 because the log to the base 10 of 10 is 1, and 4.76 plus 1 last time I checked was 5.76. And so this means that when I'm 1 pH unit, this is what I want you guys to write down and remember. When I'm 1 pH unit greater than the pKa, 90% of what I have is the anion. Okay? This means that 1 pH unit, I'll write it down, 1 pH unit greater than the pKa, I'm 90% unprotonated. Okay? Suppose I'm 2 pH units greater than the pKa. Okay? Then I'm talking about 6.76 equals 4.76 plus the logarithm of the acetate anion divided by the undissociated acetic acid. And this ratio, therefore, would be what? 100, right? The ratio is 100 to 1. And this means that when I'm 2 pH units above the pKa, now I'm 99% unprotonated. Let's do one more example. Consider 1 pH unit below the pKa. Okay? So that means my pH is 3.76. That must equal 4.76, the pKa of acetic acid, plus the logarithm of the acetate anion concentration divided by the undissociated acetic acid. And once again, you're going to tell me, choose a different color, what the ratio of this must be. So what's the ratio equal to? I can't hear you. 1 to 10, right? Because last time I checked, the logarithm of 1/10 is -1, and 4.76 minus 1 is 3.76. And so the punchline that I want you to remember here is that at 1 pH unit below the pKa, 90% is protonated. 90% of the acid is protonated. By the same token, if I'm 2 pH units below the pKa, what percentage of the acid is going to be in the protonated form? 99%.